Our first example of using the delta function in an ODE is going to be that we consider the problem of trying to solve y double prime plus y equal to 4 delta of t minus 2 pi for y of 0 equal 1 and y prime of 0 equals 0. And I'd just like to note that this is the same differential equation as you'd have for an undamped spring with forcing term given by the right-hand side for delta of t minus 2 pi. So that forcing term is going to be like you give one big push to the spring at the time exactly 2 pi, and then you don't do anything else. And our initial conditions are saying that at time 0 we start by like stretching that spring some unit 1 and then releasing it from rest. And I just want you to think about that as we see the terms that come out of the solution. So first off, we're going to set the Laplace transform of both sides equal to each other because that's how we start every Laplace transform differential equation problem. And then we just have to compute what that Laplace is on both sides. So I'm going to start with the left. L of y double prime plus y. We usually did x's for springs, but I don't like having to write those capital X's, so we're doing y today. Second derivative is s squared times our Laplace variable minus s times our initial condition minus 1 times our second initial condition. And then Laplace of y is just capital Y. And so plugging in our values, we would get s squared y minus s times 1, and the y prime of 0 goes away, plus y. And then our Laplace of 4 delta t minus 2 pi, we actually took in the last video. It's 4 e to minus 2 pi s. So I'm not going to show that again. We just know that that's what our Laplace of y double prime plus y is going to be set equal to. So all I did was I plugged in that Laplace transform we already calculated. I wonder if I can make the scribble work intentionally. Yeah, okay. Great. So once those two things are equal, we can go ahead and solve for y. So I've got that s squared plus 1 times y minus s would be what's on the left side is equal to 4 e to minus 2 pi s on the right. Or isolating y, I move that s over to be with the 4 e to minus 2 pi s. And then I just divide by the thing that multiplies y, in this case s squared plus 1, into both terms. And now we're to the working backwards part. We know what capital Y is, and we want to take the inverse Laplace transform of that in order to get our solution. And I'm again going to go ahead and move to the next slide to do that because I don't want to have to switch and only have one line. So hit pause if you're still writing here. But I am thinking about taking L inverse of the capital Y that I wrote down, which is 4 e to minus 2 pi s over s squared plus 1 plus s over s squared plus 1. And so I would break this up by linearity. Inverse Laplace of the first term plus inverse Laplace of the second term. And I'll go ahead and note that I already know L inverse of s over s squared plus 1. This is one of those cosine type terms because I have s squared plus something squared on bottom and s on top. And in this case, I'm just looking at k equal 1, so this is just a cosine of t. And then L inverse of 4e to minus 2 pi s over s squared plus 1. Sorry. I'm going to be able to pull a 4 out and be looking at L inverse of 1 over s squared plus 1 times e to minus 2 pi s. All I did was like separate out the fraction part and the exponential part. And the reason for that is because I want it to look like a Laplace inverse that we already know, which is f times e to minus as gives us f of t minus a u of t minus a. We didn't cover it in this section, but it's actually going to always show up whenever we use a delta function. So for the way I've represented this, we can see that our big F is this thing right here, which corresponds to a sine t type function. And then our a is going to be that 2 pi that's in the negative exponential. So then our f of t minus a is going to be sine, and then instead of plugging in t, we plug in t minus 2 pi. So then this inverse Laplace transform is just sine of t minus 2 pi u of t minus a, or t minus 2 pi. So then, our y was the sum of those two inverses put together. So we had that cosine t plus 4 sine of, sorry, in your skeleton notes it's in the opposite order, and I do not want to mess you all up here. It's 4 sine of t minus 2 pi u of t minus 2 pi plus cosine t. And those are the functions that define y, our solution. So once you've got all that written down, I want to talk about what these terms actually mean. So this cosine t is the same kind of solution we got out of our undamped spring problems when we were looking at constant coefficients, where we didn't have a damping term on our middle derivative. We got cosine terms and sine terms and no exponentials. Those are solutions to things that look like y double prime plus y equal to 0. So this cosine t that happens for any t is just describing the regular oscillation of the spring from the place where we released it, assuming that there's no friction. Then this term right here is going to start after t equal to 2 pi. So remember, u is one of those step functions, Heaviside functions. It's an on-off switch, and it doesn't start until t crosses the a value. So when t is 2 pi, this function begins to exist, and before that it's 0. And it's just describing the forcing push that happened at that time, t equal 2 pi, which was defined by that 4 delta at t minus t0, t0, 2 pi. So it's kind of cool. And then I do want to note that once u starts to exist, like it's switched from 0 to 1, this function is always going to be here. So that delta function happened at a single instant, but then we're going to see the result of it, this 4 sine t minus 2 pi, in solution for all time after 2 pi. And I think I'm gonna pause here and then start another video that talks about like mathematically why that's happening in more detail. So I will see you in the next video.